Alright, so the slides are from CS230, Stanford University, prepared by deeplearning.ai. Now, we were looking at case studies. So, the first one that we looked at was LXNet, of course LANet, then LXNet, then VGG, and then in the last class we talked about ResNets. You will see all of them bring a different idea, a new idea, but very quickly superseded by a newer idea. Okay. So, as we talked about before, what is AI? This is AI, right? And this is what your model is. So, your model takes the input, most of the times, until now, and in fact in this course we will not be talking about unsupervised learning per se. So, this is input, this is output, they are always given to you because it is supervised learning, and this is what you learn as a neural network, right. So, in our case F is very specific, it has to be a neural network, right. So, this is your neural network, these are your inputs, and finally you have C classes. So, this is that function that transforms input to output, and you can design here whatever. There are absolutely no regulations, no laws except some mathematical constraints, like you should have matrix multiplications and so on, right. Otherwise there are absolutely no constraints. We talked about LANet 5 and parameters in this, we talked about LXNet, VGG, and what do they bring? This, as I said in the last class, is a super important topic. They are there everywhere in today's deep learning. So, even though architectures might change, right, how you take convolutions might change, but this guy has stuck there. So, residual blocks are always there as it stands of today. Now, we were talking about this, that training error. So, important here is that this is not validation error, it is the training error itself that starts increasing after a certain number of layers. With ResNets, it behaves as we expect it to. So, we were talking about ResNets in the last class, and we do not have slides here. Anyway, so what we had done was, so what is this whole thing, एक बार वापस लिखवाना. So we had AL and so AL plus 2 will be ReLU of no, not I don't want Z, I want W's, I want B's, and I want A's. So WL plus 2, and then I should have AL plus 1. So this gives me Z L plus B L plus 2 plus AL. This is what you get. Okay. Now, if you want, so if you have something like this, in that case, what have you just learnt? This is your identity function, right? AL plus 2 is same as AL. How can you do that? So if this guy goes to 0 and if this guy goes to 0, right, then basically AL2 plus will be same as AL, because AL itself was the elude quantity, so that was all positive and this will be all positive, so this is fine. Now you can think of it this way, that in case of without ResNets, right, system was not even able to make things 0. Why, we don't understand, at least I don't understand. I have not seen any paper that talks about this in very much detail, or at least I have not come across. So if these guys become 0, AL plus 2 is same as AL. So something as simple as this happens, and now what will happen? Even if you keep on increasing the number of layers, right? If I was doing better at some previous layer, I will keep on continuing that output and I will not worsen it. So that's how. Any questions here? Now I'll briefly talk about now, don't go to notations, just just think of what is this quantity, because notations are not matching with the rest of the class. Or YL actually. Right. So we talked about this very vaguely yesterday. When you write gradients, okay, so let's say if you are looking for gradients for 1, in general this is how they would look like, right? These terms we know what they are, right? Every term is del A by del Z and then del Z by del A again, okay, in this length, okay. Now without ResNets, this is how your gradients look like. If a lot of these terms are less than 0, gradient will vanish. If a lot of these gradients are greater than 1, so then it will explode, okay. Now exploding gradient we know how to take care of, just gradient clipping. With ResNets your gradients look something like this, right. So even if these guys they go to 0, you have identity there. So there is somebody that is taking care of the fact that even if there are gradients that goes to 0, this term will not go to 0. So gradients will keep on passing. It does not matter how backward you are in time, and this is a very super result. This is what you were looking for. You can actually translate gradients from even 100th layer to all the way until 1. And now you would understand I don't really need this kind of a, so I don't really need these kind of transitions like many of you were asking yesterday. Of course we can do them. So of course it's okay to do this, but it is not needed. In fact this is worse than this guy. Why is this worse than that? Why is this worse than this in some sense? In some sense, because you can always come up with a counter argument that this is better for some reason. See, here it gives you a bigger chain. So you will still have a larger chain, and if there are numbers that are small, their multiplication will not go to 0 but will become small enough. Whereas if you skipped in this manner, right, then you are skipping every next layer. So you can't do better than this. You can't skip something lesser than 1, okay. So you can't have this continuous chain of gradients that will be multiplied lesser than those numbers. Questions here? Okay. So we are done talking about ResNet unless you have questions. Yes, done? Chalo. Alright, so now we talk and network in 1x1 convolution. So what do you think 1x1 convolution would do? Yes, what do you think 1x1 convolution would do? If this is a volume of size 3 x 3 x 8, if I take its convolution with 1x1 filter, is this meaningful? Why not? It is just a number that you are multiplying with, right? So it does not make sense if it is 3 x 3 x 1, but if it is 3 x 3 x 8, this will be 1 x 1 x 8 and it makes sense. Okay, what will be the output size? Just give me the size of the output. It will be 3 x 3 x 8, not 8, it will be 3 x 3, because if number of channels are 8, then this becomes 8. Okay, so 3 x 3 x 8, 1 x 1 x 8, and what you get is 3 x 3. So this actually makes sense, and you don't need to do what? You don't need to do same padding. You already have a way to compute convolutions such that the length and the breadth of the volume are unchanged. Okay. So if you take just 6 x 6 x 1, it's just a number that gets multiplied with everything, which does not make sense. But if it's a volume 6 x 6 x 32, and if you multiply it with, if you take convolution with 1 x 1 x 32, what you will get is 6 x 6 and cross the number of filters here. Okay. And we have again seen how do we convert CNNs to DNNs. So try to convert how does this 1 cross 1 convolution look like. Okay. Where are you actually multiplying? All right. Using 1 cross 1 convolutions. So this is 28 cross 28 cross 192. If you do this, convolution with 1 cross 1, number of filters is 32, what will be the output size? 28 cross 28 cross 32, right? So 28 cross 28 cross 32. If you remove 32 and if you actually have 192 filters, then 28 cross 28 cross 192. So it's very easy to take the same, it's very easy to get input volume same as output volume. You don't need to do same padding, right? Just convolution takes care of phase and the number of channels take care of the third dimension. So 1 cross 1 cross 192 and that's it. So is this fine? Now Inception network. How many of you have heard of it? So again, it was in 2014 by Google, if I remember it right. So this is the motivation for Inception network. 28 cross 28 cross 192. This is your input volume. You have to explain me how are you making is 28 cross 28 cross 256 from this. As I said before, deep learning is all about, in Hindi we call it jugaad, but somehow making things work. So what new thing do you see here? So until now, what was there in LXNet? LXNet just enabled deep learning for large data sets. Okay. So their contribution is huge in that sense that they were the first one to do that for such a large data set. Done. Then what does VGG come and tell you? VGG comes and says you can be consistent, you can still have a lot of layers and do better than LXNet. So they say you can be consistent and still be better than LXNet. So you don't have to really figure out ki my filter size has to be 11 cross 11 in this layer or 7 cross 7 or 5 cross 5 or whatever. Right? What does ResNet solve? ResNet solves a very fundamental problem. So VGG 19, VGG 16, VGG 22, they couldn't scale beyond that. Okay? But ResNet says you can have as many layers as you want provided you have skip connections. Okay? Inception is a different thing. It says until now you have been doing like this. First volume, do a certain kind of convolution 5 cross 5, get a output volume and then take ReLU and then get a max pooling or whatever. Okay. Inception does it in a very different way. It simply says 1 cross 1 network, 1 cross 1 convolution. So if I take 28 cross 28 cross 192, 1 cross 1 and 64 filters, how much will I get? This one. So this green is done. Okay. Now how will you get this blue one? 3 cross 3, padding is same. So if padding is same, you get 28 cross 28 cross. So 28 cross 28 remains. How many filters do I need? 128. So this part is done. Similarly for 5 cross 5 cross, what will be the filter size? 5 cross 5 cross 192. So 5 cross 5 cross 192 is the filter size and how many of them? 32 of them, and what you get is this one. How do you get this one? So here we have some kind of a problem. Okay, here if you see, even if I take same max pool, I take stride of 1, I can take care of 28 cross 28. But we have seen, what does max pooling do? It does not touch this dimension the way we know it. Tomorrow if you define max pooling in a different way, that will be a legible way of, that will be the okay way of doing it, provided you can code and prove that, provided you can code and for that particular data set show that it works better than the traditional max pool. You can make whatever changes you want, provided you are able to code, handle that code and show that it has better performance. This is all is needed. So max pool, we need to do something here, okay, but it's a simple trick, we'll talk about it. Finally 28 cross 28 cross 192, and you get 28 cross 28 cross 32. How can I get this volume otherwise without doing all these combinations? How can we get this volume otherwise? Give me something else which is not here. Sorry? So 1 cross 1 I have here. I am saying give me something that is not here. आसान है यार, say whatever. I mean some convolution filter size that is not here. Do some convolution that is not here and get this one. Like, so 7 cross 7, 7 cross 7, padding same. 7 cross 7 cross 192 actually, padding same, and then how many of them? 256, we will get this one. So there are so many ways to get this number, and will all these numbers be same? If I do 7 cross 7 cross 192 and if I use 256 of them, output volume will I get, even though dimensions are the same? Will the numbers be same? Will the volumes be same? No, they will be different numbers, right? So this volume will be different from this one, but you can get a volume of the same size. Okay, so you can just get a volume of the same size, but not the volume itself. Okay. Any questions in this except this part? We'll come back to this. There is a very small trick to it. Maybe you can use 1 cross, this is what they do, they will use 1 cross 1 to reduce this size to 32. Okay. So until now we have just seen, give me an input volume, use any one of these top 3 or something else, get an output volume, take ReLU and do max pooling. GoogleNet comes and says, I want to do all. Now, why do they do it this way? Okay, so there must be something in their mind. So, the problem of computational cost. Get this number 120 million for me. It's a simple question is this, you have input volume of size 28 cross 28 cross 192. You are doing convolution with a filter of size 5 cross 5, padding is same, number is number of filter is 32. So you get 28 cross 28 cross 32. Question is, how many multiplications are taking place? How many multiplications are taking place? For every one value here, how many multiplications are happening? For this one value, you will have 28 cross 28 cross 192 or something else? For one value here, you will multiply 5 cross 5 cross 192 numbers with there. So this many numbers are getting multiplied for one number. How many such numbers are there? 28 cross 28 cross 32. So this is the total number of multiplications you get, which is 120 million. Just look at it for maybe 5-10 seconds. Is this fine? For every number here you are multiplying as many numbers as there are weights in your filter. Okay? So you have this many multiplications. You are going from 28 cross 28 cross 192 to 28 cross 28 cross 32. Tell me what is happening in this case now. Output size is final output size is 28 cross 28 cross 32, which is same as this one. But if you get it some other way, will you get the same set of numbers? Of course not. Only the size will be same. So now tell me how many total multiplications are happening here. Instead of 120 million, it is 12.4 million now. Just 1 by 10. So you start with 28 cross 28 cross 192. Convolution 1 cross 1 and 16 such filters. So my filter size will be, so for every number here, how many multiplications will I make? 1 cross 192. How many such numbers are there? This many. So when you multiply this, you get 2.4 m. Now you go from here to here. 5 cross 5 cross 16. So 5 cross 5 cross 16 for every number here. How many such numbers are there? 28 cross 28 cross 32. You multiply that, you get 10 million, and add them, you get 12.4. Any questions here? There should be. There can be a question that, no, but unless you ask, I won't answer. So just think over it. I mean, why did you choose 16 here? Just choose 32. And instead of 12.4 million, you will settle with just 4.8 million, just double of it, right? So you could even further reduce it. Why did not you do that? That's a question I am asking you. Did you get the question? Question is, I was just supposed to go to 28 cross 28 cross 192 to 28 cross 28 cross 32. I first used 1 cross 1 convolution and then used 5 cross 5. This one increases my number of multiplications. If instead I use 32 filters here, I will just have to multiply this number with 2. Instead of 13 I will have, instead of 16 I will have 32. So this will be 4.8 m and not 12.4 m. Why are we not doing that? Think over it and we go next. Now inception network. So this is an inception module, and inception network consists of lots of inception modules. Tell me what is happening here and how is it related to this particular slide. You do 1 cross 1 and then you do something cross something which is not 1 cross 1. So you actually did that. You also used just 1 cross 1 to get this volume and then you start taking a combination. Okay. So previous activation is 28 cross 28 cross 192, you do it with 1 cross 1 convolution, you get something. So you finally get this one. Have we understood this one and this one as well? Just do the first one, 28 cross 28 cross 192, and if I do 1 cross 1 cross, what will be here? 192, how many of them? 64. So 64 of them and I get this one. What about this guy? So 28 cross 28 cross 192, 1 cross 1 with, and this is inception module. You say why this number? Authors chose it, right? You go and want to choose something else, feel free to do that. 96 and then again 3 cross 3. So you finally what do you get? 128. How many filters of this size will be there? 128. What will be the size? Three cross 96. Okay. How many of them? 128 and you get this one. Similarly for this one, I am not doing that. Let us do the last one. You do it. Yes. 28 cross 192. Max pool. Filter size is 3 cross 3. Instead of stride 3 or 2, you take stride equal to 1. So first of all, tell me how much padding will I need? How much padding will I need? 1. Why 1? N plus 2p, that will make it 30. Stride is 1. So N plus 2p minus f plus 1. Yes or no? Right? So it was n plus f minus 1, this becomes n plus 2p, so this becomes 30, n minus f plus 1, so minus 3, this becomes 27 plus 1, 28. So these are the specifications. Pooling is 1, stride is 1, convolution size is 3 cross 3, and then you finally, so what will be my output size here? 28 cross 192, because the way we know max pooling until now, it does not touch the depth. Okay. So this is what we have, but what we want is 28 cross 32. This is what we want. So how do we get this? By now you must have understood कि जुगाड़ करना है. Somehow you want to go from this volume to that volume. Now you can easily give me, this is your input volume, this is the filter size. How will you get 28 cross 32? 1 cross 192. How many of them? 32, and this is what you get. Okay. This is an inception module. and wait. So, see all authors, almost all authors at Google except one. So, this is the inception module. Okay. Now, can we rotate this? Yes. Right. So, the problem with the slides is that you don't see these things there. Okay. So, I will first talk about this thing and then I will switch to the paper. So, or maybe paper you can read better, yes. So, tell me what is happening. How do I get rid of this? Huh. So, at the back, I mean not at the back, somewhere, can you see this at the first row? Okay. See what is happening here? You get the input, okay, and this is your softmax over 1000 classes. Which data set are we talking about? Which data set are we talking about? ImageNet, okay. How many images are there in ImageNet? 1.2 million with 1000 classes, and all these papers are just improving the state of the art. Okay, do convolutions in a new way and improve the state of the art. This is input, this is output. So, what is my function f that maps input to output? This whole thing except the input and output. Okay. So, this whole thing is my network or function, AI, whatever you call it. This one thing, if you see, is what? This is one inception module. So, you see there are so many of them, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. What you would be doing here? So, you average pool, okay, fully connected layer, and then finally softmax. Okay. So, this is the normal trend you will see. It does not matter what you do in the beginning, but towards the end you will have a fully connected layer and then finally softmax, because until today we do not know how to do multi-class classification better than using softmax. Okay. So, softmax, you see enough inception modules here. Now, question here is, if you see this module is exactly same here as well and here as well, except that you have a couple of fully connected layer extra. So, you have one extra fully connected layers here. My question is, why would you like to have them here? So, input, inception, 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 finally take pooling and then softmax, and you are done. Why would you like to do these things? So these things that are not visible there are basically same as these guys. I will stay here now. Yes. What do you think could be answer to this? So output was taken here. What effect these guys might be having here? Because all I am having here is this same thing. Maybe one fully connected layer is extra, but essentially the same thing. Okay. Finally, you have a softmax here, and finally you have a softmax here. Can this help us with overfitting? Right. So almost every deep learning paper that you will see, at least the between 2012 to 2016-17 ones, every paper will invariably introduce a new architecture and will have something to say about this particular thing has a regularization effect. So if you see here, if you take output just here itself, right, this is your function. Is this simpler than this whole big thing? So if your output is taken just here itself, then it has a regularizing effect. Same for this, and finally if you go all the way until there, you go all the way until there. So if you start taking outputs earlier, right, that has a regularizing effect. So for some inputs, maybe you would like to travel all the way until here, but for some of the inputs or for some of the examples, maybe it is better to take exit somewhere earlier and not all the way, go all the way until there. Okay. So this reduces overfitting and makes network work better. Any questions in this? So, and the paper, so the paper actually cites this meme, okay, that what inspired them to come up with this particular network is this meme. Any questions in this? So all we are trying to say here is, so imagine whatever you can, code it and prove that it works better than the previous approaches, and you are done. Okay, and it's very easy to say, but you need to be at Google to do that. All right, so